Problem number 4 says that a student stands at the edge of a cliff and throws a stone horizontally over the edge with a speed of 18 meters per second. The cliff is 50 meters above a flat horizontal beach. So this problem is going to ask us for two things. The first part is how long after being released does the stone strike the beach below the cliff. So what we're looking for is the total time of flight that it takes for the stone to make that distance of 50 meters. The second part of the problem is going to ask us to solve for the velocity vector of the stone. So let's take a look at part A. How long after being released does the stone strike the beach below the cliff? So we look through our toolbox of relationships, and since we're looking for the vertical component, that of the y direction, what we're going to do is choose a relationship that has a distance in the y direction that we can calculate, and use the fact that we know that the initial velocity in the y direction is 0. Okay, so if we choose the relationship that the change in the y direction is equal to the initial velocity in the y direction times time, and we add to that 1/2 of the gravity times time squared, that's our acceleration function, we have values here that we can use to solve for that time of flight. So inserting the 0 then into the velocity in the y direction simplifies the expression, and we now have the change in the y direction, that's the distance from the top to the bottom, is equal to 1/2 the gravity times time squared. So we can move terms around here a little bit, simplify them so that we can get time, the t, by itself. So if we bring the 2 over to the other side of the relationship, we have 2 times the change in distance is equal to gravity times time squared. And then one more manipulation where we move gravity into the denominator onto the other side. So now we have time squared by itself as a single term, and we can take the square root then of both sides, and in doing so now we have the square root of 2 times the change in y divided by gravity. So now we're ready to insert all of our known values. 2 times minus 50, which is in the downward direction, divided by the downward direction of gravity, 9.8 meters per second squared. This is convenient. The negative signs cancel out, and when we multiply the terms together, 100 meters divided by 9.8 meters per second squared, take the square root of that, we end up with a time of flight now of 3.19 seconds. For the other portion then, the B portion, with what speed and angle of impact does the stone land? So this is the one where we're going to end up calculating for our velocity vector. So first let's look at the velocity component in the x direction, v sub x. We were told in the problem that the stone was thrown with an initial velocity of 18 meters per second. That is our x component of velocity. In the y direction then, the relationship that we're going to choose then is solving for the y component of velocity and setting that equal to the initial component of velocity in the y direction added to the acceleration or the of y or g times t. Okay? So now as we start populating the right side of the expression, the initial velocity in the y direction starts off at 0. Everything is in the x direction. 9.8 meters per second squared negative, that's our acceleration of gravity, times the 3.19 seconds that we calculated in part A. That was the time of flight for the rock to cover that 50 meters. So now we multiply this through, we have a velocity now that we've solved for in the y direction of minus 31.3 meters per second. Minus because the rock is traveling in a downward direction. So now what we need to do is calculate that velocity vector to determine the speed and the angle. So now we have both of our x and y components of velocity that we can use again in the Pythagorean theorem to come up with that vector magnitude that we need to solve for. So 18 meters per second squared added to 31.3 meters per second squared, add them, take the square root, and now we have a magnitude of 36.1 meters per second, which is the magnitude of our velocity vector. Now we need to solve for the angle because they've asked for the angle of the impact. We're going to use our relationship that says the tangent of theta is equal to the velocity in the y direction divided by the velocity in the x direction. I can take the inverse tangent of both sides of that expression so that now I have just the angle by itself. The inverse tangent then of the velocity in the y direction divided by the velocity in the x direction. So minus 31.3 meters per second divided by 18 meters per second gives me a value then when I take the inverse tangent or the arctangent of an angle of minus 60.1 degrees. So our velocity vector then tells us when we combine the two terms a magnitude of 36.1 meters per second at an angle of 60.1 degrees below the horizon because it's a negative value.